Really appreciate everybody's patience. Okay, by now we all know language models, but what comes next? Jason Huang has declared physical AI that acts in the real world is the next wave of artificial intelligence and the foundation of the next industrial revolution. Okay, let me admit one more. Okay, perfect. Yeah, it's highly related to almost everybody in our program, not only for our research, for example, in engineering and various wet lab automations, but also for your career, especially for our young folks. As you always want to know where is the beef, and smart work is much more important than hard work. Okay, if that still feels far away, simply follow the money. I mean, this Monday, okay, let me meet more people. Yeah, this Monday, UTA Robotics launched a public offering, and the IPO price there is only $22. But meanwhile, on the Hyperliquid platform, the pre-market price is already 87. I mean, 1 week ago, when I sent out the email, it's only 70, but now it's 87. It's more than tripled of the IPO price. So the field is really fast moving now, and the best time to understand it is before everyone else does. That is why we have invited the sharpest young researchers in this space, part of our network, to talk to you directly. Today, it's such a great honor to have Professor Miao Yin with us today, and he is the 2025 NVIDIA Academic Research Award recipient and also 2026 National Science Foundation Career Award recipient. And this is a rare chance to learn from someone building at the frontier of this domain. So please join me at welcoming Professor Yin from University of Texas. Thank you. And let me pass the microphone to him.
All right. Thank you, Richard. Thank you for having me, and thank you for the introduction. Okay, so today I'll talk about how we can build large-scale and efficient 3D digital twins for physical AI. I will focus on two questions. How to make the 3D representation compact, and how to train city-scale models efficiently across multiple GPUs. First, I will introduce the physical AI setting and to introduce how important the 3D representation is in the entire physical AI pipeline. Then I will present two important works from my group. So the main message is that model compactness and system scalability is to be designed together. Okay, so physical AI means that an AI system directly interact with the physical world through sensing, reasoning, and actuation. Examples include the energy systems, industrial automation, autonomous driving, and smart city monitoring, etc. The digital twin gives the AI agent a virtual environment where it can understand the current state and test possible actions. This can improve the safety, efficiency, but also create three major challenges: real-time speed, and the scalability, and the uncertainty to very large environments. So this slide shows the closed loop between the physical system, the digital twin, and the AI agent. Sensors collect the observations and data assimilation updates the digital twin so that it can reflect the latest physical state. Then the AI agent uses the twin to estimate outcomes and evaluate a policy between sending the real action back to the physical system. In an energy, for example, in an energy application, the agent can test grid optimization or storage decisions virtually before applying them practically. So the digital twin connects perception, planning, and safe actuation in one continuous loop. Here is another simple robotics example. The robot begins with target location and information such as the battery level. Um, Before moving, the agent evaluates candidate path inside the simulated environment and renders the scene from the robot's point of the view. It can then check for the obstacles, energy, and other safety constraints. Only after the simulated result looks safe does the robot execute the action in the real world. The new observations are fed back into the twin, so next decision uses a more accurate model. To build such a real-time 3D digital twin, we use the technique called 3D Gaussian splatting to construct the virtual 3D world. Images, depth, and other sensor data are used during offline learning to create a collection of Gaussian primitives. Each Gaussian stores information about its location, shape, color, and opacity, which are those learnable parameters like a neural network. For the new camera view, the Gaussians are projected into image space and combined by a differentiable tile rasterizer. Adaptive density control can add detail when the necessary the primitive removal is happened. This combination gives us a high quality rendering at a speed that is suitable for the online digital twin. Then once the model has been built, then it can complete online update. That was the basic technical view of this 3D Gaussian splatting. But when we scale 3D Gaussian splatting to a large digital twin, there are three main issues. First, the reconstruction must remain reliable when sensor measurements are noisy or incomplete. Second, a dense model may contain millions of redundant Gaussians, which are the parameters. Like there are a lot of redundancy in the neural network, so we have to do some pruning and quantization. Similarly here, most of the Gaussians are redundant, which increase memory and rendering cost. Third, the city scale training must be distributed across multiple GPUs, creating a large communication burden among those GPUs. So next part, I will address those problems in 2 stages. The first one addressed a compact and a robust representation, while the next one focuses on the scalable distributed training. So this work called a Gaussian SPA balances reconstruction accuracy, sparsity, and robustness in a single training framework. Instead of the regular pruning, just like the neural network, how we compress the neural network. Specifically, we train a dense model and prune it afterwards. That's the regular technique to reduce the model size. But in this work, the proposed method alternates between an optimization step and a specifying step throughout the training. We formulate the training objective as this optimization problem. The upper part is the regular training loss to minimize the loss, and which can guarantee the accuracy and the rendering quality. And then we add a constraint to restrict the number of Gaussians to be less than a certain value. And then we used we proposed optimization technique called simplifying optimizing technique to alternatively update those parameters. So I'll not talk about the mathematical details. Just keep in mind, so in this optimization process, weak or unnecessary Gaussians are gradually removed instead of one-shot removal. Then the remaining Gaussians continue adapting to preserve important details. So this process is gradually completed in the entire training process. So this is very smooth, and we can keep the quality, and then just gradually remove the unnecessary Gaussians. Okay, so there is an image at the bottom show that the compact model retains fine structures, and we can also see the number of Gaussians is like just 1/3 compared to the original 3D Gaussian splatting model. But you can see that the details is even better than the baseline. So this slide summarizes the quantitative benefit of the proposed Gaussian spot. On the mid-nerve 360, the model uses about just 0.55 million Gaussians instead of the original 3 million, which is roughly a six times reduction, while the PSNR improves by about 0.4 dB, which is better than the baseline. On another deep blending dataset, it achieves around 10 times fewer Gaussians together with an average PSNR gain of 0.9 dB. It also outperforms the prior compression technique called the mini splatting at comparable reduction level. The visual comparison is important. The compact model keeps detailed objects sharp and use larger Gaussians, mainly in a smooth background region. So which means after the proposed method training method, it can use a larger parameter or a single parameter to represent the entire background, but use more parameters to represent the details, the high focus and detail. Okay, so that was the work we proposed to solve the memory problem. So next, we'll talk about how to deal with the multi-GPU training in a distributed system. So in the original 3D GS technique, it reconstructs a large-scale scene and communicates Gaussian level information among multiple GPUs. So because the model is very big, so we have to distribute the parameters onto multiple GPUs instead of put the entire model on the single GPU. So, but those chips have to communicate the parameters, like how we distributed training, how we distributed train neural network, right? So that's very similar. but there are differences. So we can see that the different chart shows that when the scene grows from 10 million to 50 million Gaussians, the communication volume increases from about 200 to 800 megabytes per iteration. And the right charts show another problem. At 20 million Gaussians, increasing from 2 to 8 GPUs raise communication latency from roughly 24 to 68 milliseconds. Even though local computation become faster. Generally in a GPU scaling up, what we expected to see is that the communication becomes less and less, but in this training scenario, the phenomena is reversed. When we increase number of GPUs, the communication becomes the bottleneck. So that's a problem. So in a regular distributed training, simply adding GPUs is not enough. We need to change the representation being exchanged rather than only just optimizing the communication implementation. Okay. So to solve this challenge, so we think about the scene distribution. So in this case, the scene is divided into spatial blocks and distributed onto different GPUs. And those GPUs are responsible for different regions instead of the entire scene. For each camera view, every active GPU performs a local projection and rendering for its own partition. The partial results must then be combined in the correct depth order to form the final image. So based on this reality and the truth, so we propose the structure instead of the basic the key idea is that instead of the communication of Gaussians, we communicate the pixels. So here is a comparison. In the original distributed training pipeline, we communicate the Gaussians to the GPU, which needs the Gaussians from another part. Then we do the global blending and rendering. But in our design, we perform the local blending and rendering, and then we just communicate the local pixels to the other GPUs. So overall, each GPU first renders its local spatial partition and produce a partial color transmittance and depth view values for the relevant pixels. Then the system then exchange these compact pixel results and perform global composition in depth order. During the backpropagation, gradients return through the stored local rendering states. The key advantage is that communication now depends mainly on the image resolution instead of the total number of Gaussians in the scene. So even though we scale up, we scale the scene from the single object to the entire city, the communication is still the same, which is only relevant to the image resolution. So This decouples communication cost from the same complexity and make larger model easier to scale. So that's the basic design. And then, even though we propose this efficient pixel level communication scheme, there are still a lot of fraction of the pixels that are necessary. So the first source is the spatial redundancy. If camera FastCom does not overlap a partition, the GPU contributes 0 pixels, which account for roughly 45 to 63% in these examples. The second source is the transmittance saturation. Once earlier layers are nearly saturate, and later pixels contribute almost nothing. So, which means if there is obstacle in front of you, you cannot see anything behind it. So we can just directly remove those communications. This work predicts visible overlap regions and detects saturation during composition, then communicates only the pixels that can affect the final image. Simply speaking, so we only transmit the pixels that are useful, and remove the pixels that is unnecessary to that have no contribution to the final image. Okay, so this is the a redundancy reduction technique proposed in this work. Okay, so after reducing communication, the system also needs to avoid idle GPUs. A single camera view may use only a subset of the available GPUs, so processing one view at a time can leave a utilization near 50%. Splaxel computes the active GPU set. For each view, can group if you can group views whose GPU sets do not conflict. Just like the image at the top left, so we can see that originally at each time step, each GPU can just compute the view for V0, but actually the V0 on GPU 1 and the V0 on GPU 3 are redundant, which do not contribute to the model. So we just directly remove it. So once we remove them, those GPUs, GPU 1 and GPU 3, become idle. So that's waste, right? So we have to do some consolidation. We move the next computation, the computation of a V2, and then we kind of schedule them together at the same time slot, and then we can just compress the computation, which needs 7 steps into 8 steps to just 3 steps, right? So this technique can just solve this GPU underutilization problem. The scheduling diagrams show the transition from the original execution to the redundancy reduction, as shown on the left 2 images, and finally, as shown on the right, the result is better utilization and additionally speed up beyond communication reduction alone. So with the final technique we proposed, we achieved the further speed up. Okay. And then let's say the final results based on the proposed distributed training technique. So at scale to 120 million Gaussians and 8 GPUs across 4 city-scale datasets, the proposed Spexor achieves about 2.9 to 7.6 times speed up, while communication remains only around 10 to 20% of the iteration time. And for the 55 million Gaussian street say, training time drops from 75 hours to only 1.3 hours. And for the 120 million Gaussian big city say, it reduces from around 40 hours to just 6.4 hours. At the same time, that reconstruction quality remains comparable or even improves slightly. So the speed up does not come from a sacrifice in the fidelity. It just reduce the unnecessary communications. Okay. So the two methods address the complementary parts of the same problem. The first work, Gaussian SPA, reduces the representation size during training, which lowers memory use and rendering cost. The latter Spexor makes distributed training scalable by communicating only composition-ready pixels and scheduling views efficiently across multiple GPUs. The examples on this slide show that compact models can preserve picture quality, and that very large models can still be trained efficiently. Together, this idea suggests a broadened design principle. For practical digital twins, we should optimize the representation, rendering algorithm, and a distributed system as one integrated pipeline. All right, so that's the works from that two representative works to solve the practical problems from our group. Thank you all for listening.
Okay, thank you very much for this wonderful talk. Okay, to be frank, this is completely new to me, but when I listen to your talk, I do have two little questions. The first one is at the very beginning, in the objective function, we take the summation of accuracy and sparsity. Okay, at the very beginning, the objective function.
Oh, this one?
Yes. Okay. I'm wondering whether we can add a parameter in front of the efficiency, like lambda, to balance the impact of accuracy and efficiency given different hardware environment. I mean, probably, for example, if we have a lot of hardware available, we probably care about accuracy a lot, but if we kind of would like to get the result within a short frame, we care about sparsity a lot. So this is my first question. My second question is, I fully understand in a public thing, for example, the street, city, we cannot adjust the angles of the cameras. But for the private thing, for example, in the bedroom or office environment you showed just now, whether we can proactively adjust the view of the camera to make them orthogonal as much as we can, so we do not have to deal with the waste GPU waste problem afterwards. Yeah. So these are just my two questions. Thank you.
Thank you. Good questions. For because I think the second question is easy to answer. So I will answer the second question first. So when you gather the multi-view images, right? you don't know how to train the model afterwards. So you just like gather as many images as you can, right?
Yeah.
Because you don't know how many GPUs you will have, or and how to distribute those images or the views. So yes, you are correct. You can like just correct the views that are orthogonal, right, to avoid the problem. But in practice, you cannot image that, right? The GPU will train like this or train like this. So usually they just like gather the multi-view images like what they usually do. So yeah, but that's I think that's achievable if you consider the orthogonal the view collection, right? And uh, for the first question, so uh, are you like asking the this term, the constraint?
I'm asking the objective function about whether we can add a tuning parameter to balance the effect of accuracy and efficiency given different hardware and time constraints. Because here it is simply a summation of these two items between accuracy and efficiency. But if we can add a parameter, we can probably adjust the different objective function given different hardware availability and time availability. So
I think this objective here is is hardware or the device agnostic. So even for different different devices, we always want the model to be as small as possible. So this constraint, the A is actually the uh, called the opacity of each Gaussian. Like in a neural network, right? The parameter is actually a matrix. So we want the matrix to be as sparse as possible. So here is similar. So we want the Gaussians, all the Gaussians to be sparse. So then we can like compress the model as small as possible. Then for different device, we always want to run a smaller model on the device side. That's our purpose.
Got you. Okay. Okay. Maybe another related question. Given, okay, if we have a different setup of hardware, when we try to, for example, replicate the results, do we need to tune different parameters for the model here or no need?
I don't think it's very necessary step to do that at the algorithm level. I think that's as enough because this is different from the a neural network model. Like for the neural network model, there are metrics, right? There are matrices. There are different sparsity pattern, which can directly affect the final execution performance for different hardware, like the big GPU and a consumer GPU and a mobile GPU. So they are different. But here, the parameters is kind of sort of the array, right? They just or a list in the data structure. So it's not a matrix. So from my opinion, that the actual rendering performance or the cost is similar across multiple devices. So for this, we just compress as much as we can, and then next we can design the rendering framework from the device side, and how to reduce the GPU rendering redundancy, like and how to optimize the CUDA optimization, like that. We can also like utilize the tensor core, right? Even we use the list or array representation. So that's what we are doing actually to utilize the tensor core to accelerate the rendering process. Yeah.
Gotcha. Thank you very much. Yeah, please, Muzi. Yeah.
Hey, thank you. So thank you, Professor. This is a really good talk. I do have two questions. The first one is, I see from one of your previous slide, there are multimodal. Yes, this one. So I see you have like the point cloud. I assume it's from the LiDAR, and image, and that's probably from RGBD, some stereo camera. So for this talk, using the Gaussian splatting technique, so are you focused only on the image, or you already integrate into the sensor fusion, like using all of the point cloud plus the RGB image?
Actually, for these techniques we propose, we just focus on the image. But similarly, you can add semantics into the Gaussians, right? You can add more features. You can embed more features into each Gaussian. Then we can still use this objective to reduce the model size. Yeah.
Okay, so it focus right now only on the imagery. But the user case I see is probably mainly for the robot like task in like an industry environment, right?
Yeah.
So how do you think about like maybe later in your research, you probably will do the sensor fusion, kind of like fuse the LiDAR, like give a colorized the LiDAR point, and then rendering with the Gaussian splatting?
Yeah. Actually, we are doing like kind of the core, algorithm foundation optimization. So for the real or the practical implementation, like just like what you just said, we can definitely like apply it and to say how to optimize the real scenario in industry, like real applications. Yeah.
Yeah, thank you. So so the reason I am asking is I'm from agriculture domain industry. So so we have kind of like the similar things. We also use the Gaussian splatting.
Oh, that's
but
cool.
for RGB only. So right now we probably will develop the sensor fusion plus the Gaussian splatter. So so the reason is from practical perspective.
Yeah.
I see you will use multiple GPU, right? Like
Yeah.
8 GPU. So it would be pretty expensive, and you can also only do that offline, right? You can't do that like on the edge device, like NVIDIA, JSON Nano, something, that device. So you can't do that like in real time.
I think it's applicable to use the Jetson to online update because but I didn't talk about it in those slides, but in practice, right, for the dynamic update, you just only to update one new view or several added view instead of the entire model. That's called like a residual update. So that's another tactic. I think it's practical on a in a on device, or the edge devices. Yeah.
Okay, thank you.
Yeah, no problem.
Okay. Maybe I have another comment. Yeah, actually, I was thinking about the same question. Okay. And back to the request. I think probably in practice we can use several picture to construct a blurred or low resolution 3D image first in real time, given the computational capability constraint. But once we back from the field, once we are in the lab, we can construct the full spectrum, the high resolution one. So this kind of a two-step approach can make it probably practical. Yeah, to make sure.
that makes sense. That makes sense. And also you can use the same technique here. We just proposed, this is for multiple GPU training. But let's change the hardware platform to edge scenario, right? So in the edge, we cannot train this block in parallel, but we can train it in in series, right? So we can just put one block onto the GPU, and then train it, and then we move it to the storage, offload it to storage. Then we just upload another block from the storage or from the CPU to the GPU. We can like do it one by one instead of the at the same time. But the algorithm level, design the same. We divided them into blocks, and we communicate.
Yeah, that makes sense. That makes sense. Thank you. Okay, thank you so much. Is there any other questions?
One more question, please.
Oh, please.
Yeah.
Thank you.
Go ahead.
So from here, like this slide, I just wondering if there is any requirement for the camera, like the frame per second, you need to have like 30 frames per second, like anything less than 10, you won't consider it, or like the angles, like you can only go straight through the path. So you basically need to have different angle of the imagery, right? So do you have any requirement for the camera or imagery?
No. Here we don't consider any like algorithm constraint. What we are trying to solve is the communication problem across the multiple GPUs. So we just try to optimize it as much as possible based on the existing data set. So, but from my perspective, like more views is are better for the final rendering quality.
Yeah, I agree. Thank you.
Yeah, please, Wei Ming.
Yeah, sorry for the last minute question. Professor Yin, thanks.
No problem. Yeah.
Thanks for the presentation. I'm Wei Ming from.
Sorry. I was not able to hear you.
Probably some internet problem. Okay. I mean, Professor Hu is a professor in University of Georgia. Yeah.
Oh, Dr. Hu.
Yeah.
Nice to meet you.
Yeah. Maybe some broken internet. Yeah. Okay, let's wait him a little bit moment. Yeah, he's from the Scripps Institute of UCSD before, and afterwards he moved to University of Georgia. Also used a lot of AI for Earth modeling. Yeah. This,
that's cool. That's cool.
Yeah. Geography modeling. Okay. So he's offline. No worry. Yeah, we can always gather his question afterwards using text. I will pass the question to you via email. Okay, so if there's no other question, we can end the talk now. Again, really appreciate everybody's patience, and also really appreciate Professor Ying's excellent talk today. A lesson learned next time. Always a new link every time. Don't recycle the old link from last time. Okay, and I will also put the video recording online afterwards. Okay, thank you everybody. Bye-bye.
Thank you.
Bye.